Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning. There is one field, phi, the holophase, the single cyclic movement from which all reality unfolds. When phi differentiates, that one movement generates its first derivatives, and with them, the three dimensions appear at once: time as omega, space as k, and motion as v. From that first differentiation upward, every higher derivative is an echo of the one below it, an infinite ascent of finer and finer reflections of phi's original movement. And because the dimensions are born from that first echo, time, space, and motion also reverberate into infinity, carrying phi's unfolding into ever deeper rhythms, structures, and flows. Thus, the entire universe, every law, every pattern, every force, every particle, every phenomenon, is nothing but phi, endlessly echoing through its derivatives and their dimensional shadows. All of existence is the infinite echo of one field. Today, we listen to just one of those echoes. In our last exploration, we ascended to the second floor of the spatial tower. We met the drift of spatial pattern. We learned how textures do not just exist, they flow, they gradient, they guide. Now we climb one more step. We enter a new realm of spatial meaning, a realm where drift itself acquires shape, where slopes bend, where space itself learns to curve. We meet G, curvature meaning. If K is space's texture, and A is how that texture drifts, then G is the shape of that drift. It is the bowl of a valley, the arch of a bridge, the lens that focuses light, the orbit that wraps around the star. Today, we learn to feel this bending in the fabric of reality itself. Let us begin with something you can feel in your body. Imagine you are standing on three different hills. On the first hill, the ground is flat. You place a ball on it, and the ball does not roll. There is no slope. This is like K with no A uniform texture with no drift. On the second hill, you stand on a straight ramp. You place a ball on it, the ball rolls straight down at constant speed. There is a slope, but the slope itself does not change. It is constant. This is like A drift, but a uniform one, where the texture changes steadily. On the third hill, you stand at the edge of a bowl-shaped depression. You place a ball near the rim. The ball starts rolling slowly, then picks up speed as it goes down, then rolls up the other side, slows, stops, and rolls back. It oscillates. It is captured. Why? Because the slope itself changes. At the edge, the slope is gentle. At the bottom, the slope is steepest. The slope has a shape. That shape, that bending of the slope, is G, curvature. This simple hill analogy captures the essence of what G represents. If A tells us how the texture is drifting, G tells us how that drift itself is bending. Think about riding a bicycle. On a straight road where there is a constant slope, you pedal steadily. That is like having A, but G is zero. When you enter a curved banked turn, something deeper changes. You lean. The road does not just slope, it curves. That curvature, G, determines how you must lean to stay on the road without falling. Or consider a spoon focusing sunlight. The spoon's curved surface does not just reflect light, it bends the rays toward the point. That focusing is G in action. G is everywhere we find bending, focusing, orbiting, lensing. It shows up in the way a river meanders, the way a leaf curls, the way spacetime wraps around the planet, the way a sound wave concentrates in a whispering gallery. It is the universe's way of saying not just change, but change of change. Not just drift, but the shape of drift. In the Holophase language, if K is the noun of space and A is its adverb, then G is like the grammar rule that shapes entire sentences of motion. Think of building a spatial narrative. When you say the field has stripes, that is K. When you say the stripes grow closer toward the center, that is A. When you say the stripes curve around the center, forming concentric circles, that is G. G does not just modify, it structures. It imposes relationships. It tells patterns how to relate to themselves across space. This makes G a higher order grammatical element. While A adds nuance to local description, G adds architecture to global arrangement. It is what turns a collection of local slopes into a coherent landscape. A valley, a ridge, a saddle. In the master tree, this represents an important transition. G sits above A in the spatial tower, but it is more than just another derivative. It is often built from combinations of derivatives of A, specifically how A changes in different directions. It is where simple differentiation begins to yield rich geometric meaning. If you want to see the precise mathematical formulation of G as constructed from derivatives of K and A, you can search for Holophase on Zenodo. There you will find the scientific papers that give this audio journey its rigorous backbone. Now let us understand G operationally. What exactly is curvature and how do we measure it? Operationally, G is related to the second spatial derivative of K. If K tells us local texture, and A, the first derivative, tells us how texture changes, then G, the second derivative, tells us how that change itself changes. Imagine running your finger along a curved line. Feeling whether it is straight or wavy gives you K's basic nature. Feeling how quickly the waviness changes gives you A. Feeling whether the wave is tightening or loosening, whether the waves themselves are changing shape, gives you G. A more precise analogy is that curvature is to a slope what acceleration is to velocity. Velocity tells you how position changes. Acceleration tells you how velocity changes. Similarly, the gradient of K tells you how texture changes. G, curvature, tells you how that gradient changes. Technically, in the language of geometry, G is related to objects like the second fundamental form or the Riemann curvature tensor built from phi's derivatives. But in simple terms, G measures the failure of a local patch of space to be flat. On a flat surface, parallel lines stay parallel. On a curved surface, parallel lines can converge or diverge. G quantifies that tendency. This makes G fundamentally about geometric destiny. It dictates what happens to things moving through that space. Positive curvature, like the surface of a sphere, tends to bring trajectories together. Negative curvature, like a saddle, tends to spread them apart. Zero curvature, flat space, leaves them parallel. Like every true letter in our language, G expresses itself through all three dimensions: time, space, and motion. Let us trace its echo. In time, G manifests as the changing shape of evolving patterns. It is what makes patterns not just move, but morph in specific structured ways. Think of a drop of ink in water. At first, there is a sharp boundary. The curvature at the edge is high. As it diffuses, the boundary softens and curvature decreases. The rate at which curvature decreases follows specific laws. Or consider a star collapsing under its own gravity. Initially, it is roughly spherical, with positive curvature. As it collapses, curvature increases at the center. The increasing curvature accelerates the collapse, creating a feedback loop. In time, G gives geometry its dynamics. Curvature is not static, it evolves, and its evolution drives further change. This is central to general relativity, where the curvature of spacetime itself evolves according to the distribution of mass and energy. In its own dimension, space, G appears as the map of bending itself. It creates landscapes where space is not just textured or drifting, but actively curved. Imagine Earth's surface. At a mountain peak, curvature is strongly positive. Space bends tightly. In a valley, curvature is also positive, but with a different shape and scale. On a saddle between mountains, curvature is negative. On the open ocean, far from features, curvature is close to zero. Or consider a magnifying glass. At the center, curvature is maximum. Toward the edges, curvature decreases. The spatial variation of curvature creates the focusing power of the lens. Spatially, G tells us where space bends, focuses, spreads, or twists. It creates gravitational wells, optical lenses, acoustic focusing chambers, and even economic basins of attraction. It is the architect of basins and peaks in every kind of landscape. In motion, G reveals itself most powerfully. It guides everything that moves. Think of a satellite orbiting Earth. Earth's mass creates spacetime curvature, G-like structure, around it. The satellite follows that curvature. It falls along a curved geodesic. The orbit is not a force pulling the satellite sideways in some mysterious way. It is the shape of space telling the satellite how to move. Or consider a marble rolling in a bowl. The bowl's curvature, G, dictates the marble's path. The marble oscillates with a frequency determined by the curvature. If the bowl were perfectly parabolic, the oscillations would be isochronous. All small oscillations would take the same time, a property directly tied to the curvature. In terms of motion, G is what makes trajectories bend even when no obvious sideways push is present. It explains why light bends near the sun, why cars lean in banked turns, and why water spirals down a drain. Motion becomes geometry made visible. Let us now locate G precisely in our growing map of the language. Recall our journey through Chapter 3, Second-Order Semantics. We met alpha, temporal acceleration above omega. We met A, spatial drift above K. Now we meet G, spatial curvature above A in a sense. But G is special. It is not just the next derivative in a simple linear chain. It is often a combination of derivatives of A in different directions. It sits at a convergence point in the spatial tower. Think of the spatial tower branching. From K, we get A, the first derivatives in various directions. From A, we get multiple second derivatives. G emerges from specific combinations of these second derivatives, the combinations that measure genuine bending rather than just arbitrary directional change. This makes G a synthesizer. It takes the raw information of how K changes in various directions and extracts the invariant geometric essence. How much is this space actually curved? In the full architecture of the language, G is a central node. Many forces and phenomena connect through it. It is the bridge between local texture and global geometry. G lives at a rich intersection in the master tree. With its immediate precursor, G is built from how A itself changes. You cannot have meaningful curvature without first having gradients. However, G is more than just the change of A. It is the geometric part of that change. With upcoming spatial branches, G provides the foundation for concepts like convergence and divergence, which are specific manifestations of curvature, where positive curvature often leads to convergence. It also underpins shear and twist, which describe other aspects of how gradients change, and higher curvature derivatives describing how curvature itself changes. With V, motion, there is a particularly profound connection. G directly determines geodesics, the natural paths of motion in curved space. In many ways, G is force in geometric clothing. Instead of saying mass tells spacetime how to curve, curvature tells mass how to move, we can say in the Holophase language, Phi's derivatives tell spacetime how to curve, and curvature tells V structures how to move. With gravity, this becomes especially important. In the Holophase framework, gravitational phenomena emerge from G-like structures in Phi's derivatives. Mass energy distributions affect Phi's patterns, which affect curvature, G, which in turn guides motion. This provides a unified language for what general relativity describes. With optics, lens equations are essentially relationships between curvature, G of the lens surface or refractive index profile, and the bending of light rays, V. This entire network shows G's central role. It is where geometry becomes physics, where the description of shape turns into the prediction of motion. What kind of meaning does G carry in reality's conversation? G says, space bends, space focuses, space orbits. While A gives space directionality, G gives space consequence. It is the universe's way of saying not just how things change, but how that change accumulates into destiny. Not just gradient, but basin. Not just slope, but valley. The semantic role of G is geometric inevitability. It tells stories whose endings are implied by their shape. This allows the holophase language to express confinement and binding, where positive curvature traps things, focusing and imaging, where curvature directs flows to points, orbital dynamics, where curvature creates closed paths, stability and instability, where certain curvatures stabilize patterns while others destabilize them, and topological constraints, where curvature integrated over closed surfaces gives topological invariance. G introduces geometric memory into physics. A curved space remembers its shape, and that shape determines future possibilities. This memory becomes the basis for stable structures, atoms, planets, galaxies, that persist because their geometry creates natural basins. In the full language, G is the architect of persistent form. It is what turns stuff moves into stuff moves in orbits, in bound states, in focused beams. It is the grammar that writes sentences of stability. As always in this journey, we test. We ask, how does curvature behave, and how can we know it is truly there? Let us talk about stability, variability, and falsifiability. Constant curvature represents homogeneous geometric landscapes. A perfect sphere with constant positive curvature, a perfect saddle with constant negative curvature, and flat space with zero curvature. These are highly symmetric and often correspond to equilibrium states in physics, the cosmic scale factor in cosmology, the equilibrium shapes of soap bubbles, or approximate uniform gravitational fields. Most interesting spaces, however, have varying curvature. Earth's surface has curvature that varies with topography. A gravitational field around a non-spherical mass has curvature that changes from place to place. An optical lens with aspherical design has curvature that changes across its surface. The economic landscape of opportunities can also be thought of as having varying curvature. When curvature varies, we get tidal forces, lens aberrations, and complex orbital precessions. The variation of G itself becomes a new layer of description. Curvature, G, makes specific, testable predictions. One class of tests is geodesic deviation tests. You place two initially parallel trajectories in the space and measure whether they converge, diverge, or stay parallel. If they converge, positive curvature is indicated. If they diverge, negative curvature is indicated. If they stay parallel, curvature is near zero. This is the essence of tidal force measurements. Another class is optical tests. You pass light through a region and measure whether it focuses to a point, spreads out, or travels straight. This tests curvature of optical space, the refractive index landscape. Orbital tests are another powerful tool. You observe closed orbits and note that their precession rates depend on curvature details. Their stability depends on curvature sign. And the very existence of closed orbits often requires specific curvature patterns. Finally, there are consistency tests. G derived from phi's derivatives should match G measured through geometric measurements like surveying, dynamical measurements like orbits, optical measurements like lensing, and gravitational measurements like tidal forces. A clear falsification would be measuring trajectory bending that cannot be described by any consistent curvature field derived from phi. For example, if parallel lines converge in one experiment but diverge in another under the same phi conditions, then either the measurements are wrong or our curvature concept is incomplete. The detailed experimental designs appear in the Holophase papers, but the principle stands. G makes concrete predictions about how geometry guides motion, and these predictions are exquisitely testable. Once you attune your perception, you begin to see curvature everywhere. In gravity and spacetime, planetary orbits embody curvature. The curvature of spacetime around Earth keeps the Moon in orbit. The inverse square law of gravity reflects a specific curvature pattern. Black holes are regions of extreme curvature where spacetime bends so sharply that not even light can escape. Gravitational lensing shows massive galaxies curving spacetime and bending light from behind them, creating multiple images or Einstein rings. In optics and waves, curved glass in lenses bends light rays, and the lensmaker's formula is essentially a curvature to focusing map. Mirrors, especially parabolic mirrors, focus light to a point because of their specific curvature profile. Waveguides, such as optical fibers, use curvature in the refractive index profile to confine light. Whispering galleries and parabolic dishes use curvature to concentrate sound. In fluid dynamics and materials, the meniscus of water in a tube is a curved surface where curvature creates pressure differences, known as Laplace pressure. Soap bubbles are minimal surfaces with constant mean curvature. Buckyballs and nanotubes are carbon structures whose specific curvature governs their stability. Elastic sheets bend and buckle according to curvature, which determines stress distributions and patterns of instability. In biology and geography, the curvature of the cornea and lens in the eye focuses light on the retina. Eggshells are curved for strength with minimal material. River meanders show curvature in the river's path, affecting erosion and deposition patterns. Mountain valleys have curvature that directs water flow and shapes ecosystem boundaries. In all these cases, G represents the geometry of function. Curvature is not decorative, it is functional. It focuses, strengthens, confines, and guides. To ground G in everyday experience, let us turn to some simple analogies. The classic image is the bowling ball on a mattress. You place a heavy ball on a taut mattress. The mattress curves downward. When you roll a marble near it, the marble spirals toward the ball. The curvature of the mattress, G, guides the marble's motion. Or think of driving on a bank turn on a highway. The road is banked, tilted upward on the outside. This banking is a form of curvature in the driving space. It allows you to take the curve at higher speeds without skidding. Your car naturally follows the curved path. Swinging a bucket of water in a vertical circle gives another example. When you swing the bucket, the curved path, G, creates an effective force that keeps water in the bucket even at the top. The water's inertia makes it want to go straight, but the curvature of its path guides it around. Roller coaster loops offer the same kind of lesson. At the top of a loop, the track curvature is tightest. That curvature determines the minimum speed needed to stay on track. Your feeling of weightlessness is a direct experience of following a curved path. Using a funnel is another simple image. When you pour liquid into a funnel, the funnel's curvature guides all streams toward the center. The steeper the curvature, the faster the convergence. All these analogies share one feature: shape determining fate. That is the essence of G. After today, you can begin to read G in the world around you. Look for focusing. Anywhere lines, rays, or flows converge to a point or a line. Light through a lens, water down a drain, people moving toward an entrance. Curvature is at work. Watch for orbits. Whenever something moves in a closed or repeating path, whether planets, electrons in atoms, or balls in roulette wheels, it is following curvature. Feel for basins. Wherever things naturally collect, valleys, bowls, depressions, positive curvature is present. Notice bending without an obvious push. When something changes direction without something visibly pushing it sideways, light bending in water, a planet orbiting, a car in a bank turn, curvature is guiding it. A simple practice is this. When you see something following a curved path, ask, what is curving to make it do that? Look for the curved space, not just for a force. Another practice is to trace lines on any curved surface, a ball, a bowl, a saddle, and observe how initially parallel lines behave. Their convergence or divergence reveals the curvature. You can practice by watching water spiral down a drain, observing how parallel train tracks appear to converge in the distance. This is like the curvature of visual space through perspective. Noticing how a straight stick looks bent when partly submerged in water, or feeling how you lean when turning on a bicycle. In each case, you are detecting G, the curvature of some space guiding what happens. We always return to the source. G, like every structure in this language, is just phi expressing itself through layer differentiation. We call the geometric lineage. Phi is the silent cyclic field. K is phi spatial texture. A is how that texture drifts. G is how that drift bends, the shape of the drift. No new substance is added at G. It is geometric information about phi spatial dance. It is phi saying, not only am I textured and drifting, but my drift has architecture. It has basins, it has peaks, it has orbits. This is the profound unfolding. One rhythmic movement, phi, through differentiation yields texture, K, then drift, A, then curvature, G, and from that, all the phenomena of guided motion we call forces. But it is always phi, always one field, always one cyclic movement unfolding through its derivatives, creating the appearance of space, geometry, gravity, and destiny. G shows us that physical law is geometric at root, that what we call forces are often the experience of following curved paths in a space shaped by phi's derivatives, and that an orbit is not a tether pulling a planet, but a valley in spacetime that the planet rolls along. As we conclude our meeting with G, let us place it in our journey through episode 7. We began with the whole language. We learned the first-order alphabet. We entered second-order semantics and met alpha, time's acceleration, and A, space's drift. Now we have met G, curvature meaning. We have discovered that space does not just drift, it bends. That this bending is not just shape, it is guidance. That geometry is alive with consequence. G is the gateway to geometric physics. It is where the description of shape turns into the prediction of motion, where what the space is becomes how things move in it. It is where we begin to see gravity, optics, and orbits as different dialects of the same geometric language. In our next part, we will explore a specific manifestation of curvature, convergence and divergence. Where G tells us about bending in general, convergence will tell us about focusing, where patterns concentrate or spread. We will see how this simple concept explains lenses, shocks, caustics, and the very idea of sources and sinks. But for now, hold this understanding. Space bends, space guides, space orbits. The universe is not just textured and drifting. Its textures bend into basins that capture, into lenses that focus, into valleys that guide. Whenever you see light focus through a lens, whenever you feel yourself lean in a turn, whenever you watch a planet's steady orbit, you are witnessing G. Whenever water finds the drain, whenever roads bank into curves, whenever galaxies lens distant light, you are reading G. You are witnessing the third question phi answers about itself in space. You are reading the geometric grammar that structures motion. You are feeling the guiding curve of reality itself. G is space's curvature. And curvature, as we will discover, is the beginning of law, the seed of order, the first hint of why things move as they do. Salam, and peace be upon you, until part 12.